You're watching a Channel 98 NBISD TV production.
Hello out there in TV land, welcome to Deja Vu, it's Algebra 2. As always, I'm your host, Kevin Corpy, and today we've got the final installment of Deja Vu, it's Algebra 2, Lesson 33. And for the final lesson, we're going to be doing something a little bit special. We've been talking about algebra all year long, and today we're going to be talking about algebra again, but we're going to talk about algebra on a higher level. It's the modern algebra, it's the abstract algebra. And today we're going to get a brief glimpse to the building blocks of the abstract algebra, which is not the elementary algebra that you're learning this year on the show or in high school. So I hope that sounds intriguing for you, and I hope that you join me for this very special episode of Deja Vu, it's Algebra 2. Okay, so what is this abstract algebra? Well, let's back it up a little bit and talk about something else. Okay, now there's another show out there called that geometry show, and geometry is a class that you've had also in high school. Now, in geometry, you studied some visual patterns of the world around you, ranging from obvious mathematical patterns, such as circles, squares, and pyramids, to those that are found in nature, such as the growth patterns of plants or stripes on the animal. Okay? Now, in algebra, we studied other patterns, not so much of shape, but rather of form, such as symmetry. Okay? Now, symmetry is something that we can only perceive or feel. It's not something that we actually see. Okay, so how do we actually study symmetry if we can only perceive it? Well, the only way to study the perception of symmetry is through the language of, you guessed it, mathematics. But how do we do that? Well, we must first find a very precise way of looking at symmetry, one that allows us to use formal reasoning that leads to equations and formulas. This is, in fact, really the most difficult step because it requires great insight, patience, and quite a bit of creativity. Now, you're probably wondering why I'm standing in front of this crazy-looking background. Well, there's a good reason for it. You see, this is Kurt Gödel in black and white, and of course you might recognize Johann Sebastian Bach, two remarkable geniuses in their time and even today. But since we're talking about groups today, I thought I'd kind of associate myself with this fine group of people. So the three of us collectively make this awesome group on today's show. Plus, we're also talking about symmetry, and as you can clearly see, Gödel and Bach are kind of tiled in there, and there's a certain symmetry that you can actually see in the pattern behind me. So very, very apropos background for today. So what is symmetry? Well, a casual definition would be to say that an object, whether it be a flower or the flower vase, has symmetry if it looks exactly the same from many different angles. What is that? Well, that is that after you manipulate it in a certain way, does it look exactly the same as it did before? Does it have the same position, the same size, the same shape, or the same orientation? For example, take a circle. Rotate a circle through its center through any angle, and it looks exactly the same as before. Let me show you. Here's a circle right here, a blue circle. A circle is perfectly symmetrical if you rotate it through any angle around the center. Okay? It looks exactly the same. So that's one thing that we say, the circle is symmetrical to any rotation through its center. All right? Doesn't matter what the angle is. It could be 1 degree, it could be 2 degrees, it could be 180 degrees. Now, the circle also has another type of symmetry, and the other type of symmetry is going to be the reflection across any diameter. And if you see what I'm talking about, here's the circle. The diameter is the long line that runs all the way through the middle here. You grab it on any diameter, and you flip it. Okay? Looks exactly the same. I could switch to this diameter, my fingers are at the endpoints, and flip it, and I get the same circle. Now, what I can also do is I can flip it, rotate it through any angle, pick a different diameter, flip it again. And it still comes out to be the exact same circle. So we say that a circle is highly symmetrical. It has many, many, many symmetries. Okay? And actually, that's what makes the circle very, very special. It's one of the most symmetrical objects that you'll ever encounter. Now, let's compare that to something like this, the square, okay? The square, I'll show you, is symmetrical through rotations, right? But I can't just rotate it through, say, 45 degrees. That doesn't look exactly the same, right? It looks more like a diamond now. But if I rotate it through 90 degrees or 180 degrees, or in fact any multiple of 90 degrees, it will look exactly the same. So it does have rotational symmetry, but I have to do it through a specific angle, okay? Now it also has a couple of other symmetries. Instead of reflecting it across the diameter, I can actually reflect it across either one of the two diagonals, which means grab it at the corner and reflect it. And it looks like the same square. Grab it on the other diagonal, reflect it, same square. There's also some other symmetries. If I reflect it through the lines that pass through the center point of the square, I get this. And doing it up here, I can do it this way. So the square still has many symmetries. And I could do those in many orders. So I could do a reflection, another reflection across the diagonal, and rotate it 180 degrees, and then flip it this way. And for good measure, we'll flip it one more time. And it's still the same square. So the square is also highly symmetrical, although not as symmetrical as the circle, okay? So notice that with all of those transformations, you could say, the square and the circle looked exactly the same in position and in size, okay? They were exactly the same. So that's what's called a symmetry transformation. And we can do them in multiple sequences, okay? So as with the circle, the symmetries of the square, to reiterate, are again those for which the manipulations that we do on them, the rotations and the reflections, leave the object looking exactly the same in position, shape, and orientation. Okay? So what are some other things that have symmetry? Well, my face. My face has symmetry, okay? Although not as much as a square and definitely not as much as the circle. So what does that mean? If you drew a vertical line right down my face, from my forehead through my nose, down my mouth, the left-hand side of my face would look almost exactly the same. There are some variabilities in humans, but as mathematicians, we have to study the ideal objects, okay? The left side and the right side would look exactly the same. That's called bilateral symmetry, okay? Now, we have to assume, again, the ideal version, okay? I know I'm not pretty by any means, but the left side looks like the right side. Now, if you extend the line all the way through my body from head to toe, our bodies, in fact, exhibit bilateral symmetry all the way through. And this is exactly why when you look into a mirror, it appears that your reflection kind of flips from left to right, okay? But it only appears that way because our bodies do have that bilateral symmetry. The mirror itself doesn't flip anything, okay? And if you don't believe me, lay down on your side in front of the mirror and you won't see yourself flip from left to right. I guarantee it, unless you have a trick mirror, and that doesn't count. So in general, the more manipulations that leave an object unchanged, the greater we say its symmetry is, okay? So of what we just did, the circle was the most symmetrical. That means it had the most transformations through which we could rotate it and reflect it and leave it unchanged. Now mathematically, those manipulations are called transformations, and they leave the object, what we say, invariant. That means unchanged. And if you go back to the days of geometry, that was called the isometries. It was a rigid transformation. So we're going to say now that those transformations leave the object invariant. Now to study symmetry mathematically, we're going to have to force ourselves to look at the transformations of the objects rather than the objects themselves. We're really not interested in the fact that it's a circle, the fact that it's a square. Mathematicians aren't really into that so much as the patterns created by the symmetries of those objects. Now it turns out that there is an arithmetic, if you will, of those transformations, just like there's an arithmetic on the numbers, right? The whole numbers. We can add, or we can subtract, and multiply and divide using specific rules. Okay? Well, using the idea of the arithmetic of numbers, we can actually talk about the arithmetic of the sequence of the transformations. And in effect, that arithmetic is going to generate another transformation. So we can say like a reflection followed by a rotation. That would be kind of the arithmetic. And that would produce another equivalent transformation that leaves the object unchanged. Okay? Now, both arithmetics work in a very similar fashion, but very noticeable differences as well. The study of the arithmetic of transformations is called group theory. And so that kind of what leads us to the whole thing of the guys behind, the whole picture of the guys behind me, okay? And it's higher level algebra. It's the study of the arithmetic of patterns rather than just the arithmetic of numbers, okay? That's why it's considered a field of algebra. Now, relying on the patterns in combining numbers, in group theory, we're interested in the emerging patterns of combining the symmetries. And what we essentially do is we're going from patterns to looking at patterns of those patterns to, believe it or not, looking patterns of the patterns of those patterns, okay? So essentially we're cranking it up a notch each time we do something, and we're trying to draw more general inferences from them. So now that we know what a group is, essentially, kind of, right, let's look at a very special type of group. Here we are. Any figure, or for any figure actually, the symmetry group, that's what we're calling it, the symmetry group of that figure is nothing more than the collection of all the invariant transformations, the ones that leave it unchanged. For example, the symmetry group for the circle, that whole group, now consists of all the rotations, all the reflections in any diameter, and any combination of the two, okay, or multiple combinations of the two. So what we need to do now is explore this new arithmetic of transformations with something we're familiar with now, the symmetry group of the circle. Okay, now here's where we're shifting gears. In algebra this year on the show, we've typically used little x, little y, and if we went into 3 variables, we'd be using little z. But in group theory, or in the study of the algebra of structures, we typically use capital letters, such as capital S, capital T, and capital W. So here we go. We're going to let S and T be 2 of the transformations of the circle symmetry group. Could be a reflection across a diameter, or it could be a rotation. If we apply S first and then T, we get another member of the symmetry group. If I rotate it through any angle and then reflect it across the diameter, call it S, then T, I get another transformation that's equivalent to it, okay? We denote this mathematically by using the composition notation T composed S, or T composition S. Now remember, we did S first, then T. And it looks like we do T, then S, because we typically read from left to right. But mathematically, when we do composition, we read that as T of S, which means we do S first. It takes a little bit of getting used to. Now, being a mathematician, we look for patterns, and we naturally want to see if the properties of the whole numbers, like 1, 2, 3, 4, and 5, are mirrored in combining the symmetry of the transformations. We want to look for patterns of what we're familiar with, the whole numbers, and see if we can apply that to this new situation, build on what we have previously learned. And we're going to do that right after we take this quick break to watch these public service announcements. But while you're gone, think about this. One last horrible joke. What 11-letter word do all English-speaking Americans pronounce incorrectly? The answer when you get back.
My cell phone number.
The odds of a babysitter calling 911, 1 in 1,400. The odds of a child being diagnosed with autism, 1 in 150. To learn the signs of autism, go to autismspeaks.org.
Welcome back to episode 33 of Deja Vu, it's Algebra 2. I'm your host, Kevin Corpy. Did you think about the 11-letter word that all English-speaking Americans pronounce incorrectly? The word is incorrectly. That's the word. Try it at home. I think you'll agree with me. Anyway, let's get back to group theory, okay? Looks like I've got to hurry because this group of aliens behind me look like they're ready to abduct me, right? A very nice symmetrical group of aliens, might I add, okay? Anyway, back to group theory in all seriousness, if we can do that. Here's what we want to ask ourselves as mathematicians. We take the properties of the whole numbers, which exhibit certain characteristics, and we see if they're mirrored into the transformations of these rigid these objects, these rigid structures. Now, the first question we're going to ask ourselves as mathematicians when we're dealing with groups of things is, number one, is the operation associative? Okay? That means if I have 3 operations, can I do them in any order and still arrive at the same conclusion? We denote that mathematically as T composed with S first, then compose the result with W, is that the same as composing S with W and then composing it with T? Okay, that's the associative property. If that passes, then we move on to another criteria that the whole numbers exhibit. Is there an identity element? In this case, is there an identity transformation? Now, for the whole numbers, the addition identity element is 0. You add any number to 0 and you arrive back as itself. Okay? Mathematically, we denote that as if T composed with I is equal to I composed with T, which gives us right back at T, then there exists an identity element or an identity transformation. Okay? So we need associativity. Can we compose them in any order we want? And we also need this identity element, which leaves everything unchanged when we apply it. Okay? For a circle, what would the identity element be? Well, it would be a transformation, a rotation through an angle of 0 degrees. Now, that kind of seems silly, right? Because we're not doing anything, but that's the same thing we do when we add 0 to any whole number. Okay? And the third thing that we want to look to see if we can find, once the first two pass, is there an inverse manipulation or an inverse operation? Now, if we mirror that with whole numbers, we know that if we add any number to itself, 5 plus negative 5, we get 0. 0 being the identity element for that operation. So what we want to do then is figure out, for that particular group, is there a manipulation that we can do that essentially undoes what we previously did that will get us back at what we've already determined to be the identity element. Okay? 5 plus 0 is 5, so 0 is the identity element for whole numbers under the operation of addition. And therefore, 5 plus negative 5 equaling 0 means that negative 5 is the additive inverse. Okay? But we're building this up to a much higher level, dealing with groups, in this case symmetry groups, of structures by doing transformations. Okay? That's the algebra of structures. Although we are looking at symmetries of the circle, those properties of looking at the circle hold true for the symmetry group of any figure, okay, including the diamond or the square, something that really doesn't even appear to have much form at all. And they mirror the properties of addition of whole numbers. Now, with abstraction being the most powerful tool in the mathematician's arsenal, the next step then, and this is going to be a giant step, is to really abandon the actual symmetries themselves and the objects themselves and focus strictly on the arithmetic, okay, on the algebra. The result is the completely abstract definition of the mathematical object that we call the group, which form the foundation of group theory, which is the building blocks of modern or abstract algebra. Okay? Now, in general, if we have some set, any set, doesn't matter, we'll call it big G, capital G, a set of entities, whether it's symmetry transformations of some figure or the addition of whole numbers, whatever, and we have some operation that combines any two elements, call them little x and little y. Those are back to our familiar x and y. And those are elements of the set G. To give a new element of that set, when we compose x with y, we can use the operator symbol now, which is like the asterisk. So any two elements of any set, call them x and y, if we compose those through whatever operation it is, whether it's symmetry or addition, and we get another element of that set G, we call the collection a group if the following three conditions are met. And it's the same conditions we already talked about. Number one, this is the test for group number one. Does the group exhibit associativity? That is, for all x, y, and z in G, does x star y star z equal x star y star z? In other words, if I do x and y first, then z, is that the same as doing y with z and then doing the result with x? That's the associativity property. The second one is there an element E, we're going to use E for the identity element now, in that group, such that x star E is equal to E star x, which is equaling x? That is there an identity element? Is there an identity operation? And for each element x, this is the third one, in the group, is there an element y such that when we compose x with y, x star y, or y star x, kind of the commutative thing, do we get right back at the identity element, which we're calling E? Okay? That's nothing more, again, than associativity, identity element, and an inverse existence. Those three conditions, or axioms as they're called, are called the three necessary conditions for a group. If anything that you're studying passes those three simple tests, you know that you have a group, okay? And you also know, which is a little bit beyond the scope of the time we have here today, you also know that that identity element and that inverse operator are unique, which means there's only one of them, okay? So as soon as those three things pass, you basically know it's a group, and it exhibits the same properties of any other group regardless of what you're actually studying. It exhibits the same arithmetic or the same algebra of transformations, okay? Okay, where do we go from there? I mean, that seems like a lot to take in. It is, okay? We're dealing with abstract objects. We're moving from numbers that are almost tangible to just the study of these ideas, okay? It's a very difficult thing to do, and it takes a lot of practice, okay? And this is what mathematicians are actually used to doing. They're looking at patterns, they're looking at patterns of patterns, and they're using basically their imagination as the fertile field for these objects that most people can't even visualize. Got it? All right, well, let me show you a specific group that will be a little bit more tangible for you on our final Deja review segment.
Deja review.
The way we tell time is another example of a group. Now I'm going to explain myself. In what we call clock arithmetic, which is really the seed of what we call modular arithmetic, the 12-hour clock, not the 24-hour clock, the 12-hour clock has the whole numbers 1 through 12 listed all the way around the circumference, okay? So we're going to let the numbers 1 through 12 constitute our group. 1, 2, 3, 4, 5, the whole numbers, okay, 1 through 12. And we are going to add them, so that's our operator. We're going to add them according to the rule of how we tell time. That is, we're going to return to the number 1 when we go past 12, okay? So the group is the numbers 1 through 12, and the operation is adding them according to the rules of clock, all right? Now, here's what that will look like. If we take two elements of the group, call it 9 and 6, 9 o'clock plus 6 o'clock, or 9 hours on the clock plus 6 hours on the clock. What is that? If it's 9 o'clock now, and you go 6 hours later, 9 plus 6 is equal to 3 in clock arithmetic, right? And that does look kind of strange until you actually realize that 9 o'clock plus 6 hours is nothing more than 3 o'clock, right? So if we abandon the o'clock and the hours, we essentially get 9 plus 6 equals 3, where 3 is another element of the group. It's one of the numbers on the clock face, right? So let's go ahead now that we've established what the group is and what the operation is. Let's see if it holds up to that three rigid axiom, or the three rigid axioms that every group must pass. So let's look at the first one, associativity. Let's talk about 9 o'clock, and we'll talk about 6 hours and 2 hours. So here's what we need to know. If it's 9 o'clock now, and I go 6 hours later, do that first, and then go 2 hours after that, is that in fact the same as having 6 hours plus 2 hours, which is really 8 hours, and adding that to 9 o'clock? Well, let's see. 9 plus 6, we already said, is going to be 3 o'clock. 3 o'clock plus another 2 hours puts us at 5 o'clock, right? So we get 5. Well, what if I take my 6 hours and 2 hours and add them first? That's 8 hours. What's 8 hours past 9 o'clock? Oh yeah, that's also 5 o'clock, all right? So what we're saying then by the associativity property of this new group we're calling clock arithmetic, 9 plus 6 plus 2 equals 9 plus 6 plus 2, okay? So we do pass the associativity. Clock arithmetic is associative. We still got 2 more. What else do we know? Well, we know that we need there to be an identity element, okay? So in clock arithmetic, there is no 0 o'clock, right? What time is it? 0 o'clock. Doesn't make sense. So we can't use 0 like we do for addition of the whole numbers. But anything that'll take us right back to where we were could be the identity element. And on a 12-hour clock, if it's 2 o'clock in the morning now, when will it be 2 o'clock in the afternoon? Or if it's 3 in the afternoon, when will it be 3 in the morning? 12 hours later. So believe it or not, 12 is in fact the identity element for this potential group of clock arithmetic. So what does that mean? That means 2 o'clock plus 12 hours is the same as 12 hours plus 2 o'clock, which is still 2 o'clock. Now notice in this case we're not making a distinction between AM and PM. We're just getting back to the same number. And 12 o'clock is in the set, right? It's on the face of the clock, and it leaves us right back to 2 o'clock where we started. So again, all of these have to fall. They have to be closed. Everything has to fall right back into our set of numbers. So we know it has associativity. We know now there's an identity element. We just need to look at the third one. Is there an inverse operation? Okay, well, to get the inverse in a clock arithmetic, we just want to get back to the identity element, which is 12. So how do we do that? We just travel all the way around the clock face, clockwise, until we get back to 12. So if I'm starting with 7 o'clock, what do I need to add to 7 o'clock to get to 12 o'clock? Well, it's 5 hours later, right? So 7 o'clock plus 5 hours is the same as 5 hours plus 7 o'clock, which gets us right back to 12 o'clock. So 7 plus 5 is equal to 5 plus 7, which equals 12. The identity element in clock arithmetic. So apparently there is an inverse. The unique additive inverse of 7 in clock arithmetic is 5. Okay? And they're all elements of the groups of numbers 1 through 12. Okay? So that's the idea of closure. We have to land with inside the group again. So it was associative, there was an identity element, and now we know there's an inverse. So believe it or not, the set of numbers 1 through 12, under the operation of adding them according to the typical clock, does form a group, a mathematical group. Awesome, right? Now, although clock groups are amusing, they're not of particular interest to mathematicians. But it does illustrate how the concept of group can arise in many different contexts, and it can be found hiding in all sorts of phenomena. In fact, as I mentioned earlier, the groups are the building blocks of many other algebraic structures. Now, whether you find this new algebra hard or easy, it does illustrate the incredible power and utility of abstraction in mathematics. So if tomorrow you wake up and you discover a novel new mathematical structure, and you go through those 3 steps and you determine that it is in fact a group, you know immediately that the structure has a unique identity and a unique inverse simply based on the 3 axioms of a group. Now, there is a cost to this increased efficiency, and it's that you must learn to work with highly abstract structures and with abstract patterns of abstract entities. Okay? You have to actually live inside your own imagination, which could be kind of fun, right? Now, you say that you can't do it. Well, anyone can train themselves to think abstractly, but it's hard work. It's what we do every time we learn to speak a new language. However, some people have developed an expectation that they cannot do so. They have what's called stinking thinking, right? They need a checkup from the neck up. And as with most things in life, we tend to find what we expect, right? Math is everywhere. And with that, that concludes the whole season of Deja Vu, It's Algebra 2. I've had fun spending time with you this whole year. I hope you learned something, and I appreciate you tuning in with me every single week. But we are out of time, and all good things must end, including this one. So I hope as you go outside, you enjoy the wonderful beauty of the mathematics that is, in fact, all around you. If you just take the time to look for it, it's there. Enjoy being a creative innovator in your own mind. Use your imagination to see things in a different way. See if they follow rules. See if they follow patterns. Who knows? You might invent a new branch of mathematics, a new algebraic structure, if you will. Okay? It all just it's an important part of increasing your awareness of the world around you, the world in which we live. So, having said that, I must be leaving. Until next time, I'm Kevin Corpy, reminding you, as always, to do your homework. And now I'm going to take off this bow tie. See you later.